Graphing exponential functions. Exploring graphs of exponential functions. Exponential functions follow the general shape y equals a times b to the power of x. Graph the exponential functions on the graphing calculator and match the graph to the correct function rule. To start on the graphing calculator, hit the y equals button in the top left, clear out any information from before, and reset the shade so that it's just going to graph a line. You don't have an inequality this time. Then enter the values for the function. Remember, the exponent is right there under the clear, and then the x button is next to the alpha. And if you hit the graph button, it'll take you to the graph of it. So the first one is graphed in blue, and then you can go back to y equals and enter 0.5 times 2. Hit the exponent button on the right side, and then the x next to the alpha, and then enter number 3 and number 4 as well. So number 1 is blue, number 2 is red, number 3 is green, and number 4 is magenta. Number 1 is the blue, which appears to be graph A. Number 2 is the red, which appears to be graph C. Number 3 is graphed in green, which matches graph B. And number 4 is magenta, which matches graph D. In all the functions 1 through 4 above, the base b is greater than 0. Use the graphs to make a conjecture. State the domain and range of the function if a is greater than 0. Well, let's start with the domain and range. In the ones where a is positive, we see that they are above the x-axis. So the domain is all real numbers because you can plug in any x value. And another way to write that is from negative infinity to positive infinity. The range, on the other hand, is just the positive since it's above that axis. And we're talking about the y values when we're talking about the range. So it is from 0 to positive infinity. It never will equal 0. It's always going to be slightly above 0. So we use that open bracket there. The conjecture might say something about it being above the x-axis or that the function is positive. In all of the functions, b is greater than 0. Use the graph to make a conjecture. State the domain and range of the function if a is less than 0. In the case where a was less than 0, we see that it's below the x-axis. The domain is still all real numbers because we can put in any x value along that x-axis. But the range is now from negative infinity to 0 because it's below that x-axis. So our conjecture might say something about when a is less than 0, the outputs will be negative. What is the y-intercept of the function f of x equals 0.5 times 2 to the power of x? That is graph C. If we plug in 0, 0.5 times 2 to the 0 power is 0.5 times 1, because anything to the 0 power is 1. So the y-intercept is 0.5. Or you can write it as a point, 0, 0.5. Note the similarities between the y-intercept and a. What is their relationship? A is equal to the y-intercept. What is the domain for any exponential function? All real numbers, or if you want to write it in interval notation, negative infinity to infinity. Describe the values of b for all functions y equals a times b to the power of x. B is the constant ratio. The symbol infinity represents infinity. We can describe the end behavior of a function by describing what happens to the function values as x approaches positive infinity and as x approaches negative infinity. So what's happening way out off in the distance on each end of the graph? Graph each exponential function. After graphing, identify a and b, the y-intercept, and the end behavior of the graph. A, f of x equals 2 to the power of x. Choose several values of x and generate ordered pair. So they chose -1, 0, 1, and 2. When they plug in -1, 0, 1, and 2, the outputs they get are 1/2, 1, 2, and 4. Then graph the ordered pair and connect them with a smooth curve, which they've done to the right. The y-intercept is 0, 1. End behavior, as x approaches positive infinity, the y values approach positive infinity. So as we're moving out towards the right, we are moving up towards infinity. As the x values approach negative infinity, so as we're moving to the left, the y values are getting closer and closer to 0. Using symbols only, we say as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches 0. For f of x equals 3 times 4 to the power of x, choose several values of x and generate ordered pair. When we plug in -1, that gives us 3 times 1/4 because it flips it over, which is 3/4 or 0.75 depending on how you choose to write it. If we plug in 0, 4 to the 0 power is 1. 3 times 1 is 3. If we plug in 1, 3 times 4 to the first power would be 12. And if we plug in 2, 3 times 4 to the second power, 4 to the second power is 16. 16 times 3 is 48. So we're going to graph them. -1.75. 0, 3, 112, 248. And then we're going to do a smooth curve. A is 3, B is 4, the y-intercept is at 0, 3. As x approaches infinity, so as we move to the right, y is going towards infinity. And as we move to the left, as x approaches negative infinity, y is getting closer and closer to 0. If a is greater than 0 and b is greater than 1, what is the end behavior of the graph? As x approaches infinity, y approaches infinity, and as x approaches negative infinity to the left, y is approaching 0. Describe the y-intercept of the exponential function f of x equals a times b of x in terms of a and b. Like we mentioned earlier, the y-intercept is equal to the a value. So in this case, a was 3, and the y-intercept was at 0, 3. Number 5 says graph the exponential function f of x equals 2 times 2 to the power of x. After graphing, identify a, b, and the y-intercept and end behavior of the graph. I'm going to start by plugging in -2. 2 times 2 to the -2. That gives me 1 over 2 squared, which would be 1/4. 2 times 1/4 is 2/4, or 1/2. So I'm going to put a point at -2 because that was my input, and 1/2. Then I'm going to use the input 0 in the x position. 2 to the 0 power is 1. 2 times 1 is 2. So I'm going to go over 0, up 2. Then I'm going to use the input 2. 2 times 2 squared. 2 squared is 4. 2 times 4 is 8. So I'm going to go over to 2 and up to 8. And we're going to draw a smooth curve through there. Now we need to identify A, B, the y-intercept, and the end behavior. As we move to the right, y goes towards the sky. As we move to the left, y goes to 0. You can use end behavior to discuss the behavior of a graph. Graph each exponential function. After graphing, identify A, B, the y-intercept, and the end behavior of the graph. Use end behavior to discuss the behavior of the graph. So they've taken their function, they plotted those points from their table. A is -2, B is 3, and the y-intercept we said is wherever A is, so 0, -2. And it says the end behavior as x approaches infinity, so as we move to the right, y this time is approaching -infinity because it's going towards the bottom. As x approaches -infinity, when we're moving to the left, y approaches 0. B, f of x equals -3 times 4 to the power of x. Choose several values of x and generate ordered pair. If you would like to, you can plug these into the calculator and just do the decimal version, or you can do the fraction version. It's really up to you. When we put in -1, that gives me 1/4, because we flip it over. -3 times 1/4 is -3/4, or -0.75, depending on which version you're using. -3 times 4 to the 0 power, that turns into 1, so our output is -3. -3 times 4 to the first power would just be -12. And -3 times 4 to the second power, that would be 16 times 3, but negative, so -48. Graph the ordered pair and connect them with a smooth curve. -1, -3/4, 0, -3, 1, -12, 2, -48. Then with a curve. A is -3, B is 4, the y-intercept would be 0, -3. As x approaches infinity, moving to the right, y approaches -infinity. As x approaches -infinity, y approaches 0. If A is less than 0 and B is greater than 1, what is the end behavior of the graph? So when A is a negative number and B is greater than 1, as x approaches infinity, moving to the right, y is approaching -infinity because the graph is moving down. As x approaches -infinity, when we move to the left, y approaches 0. Graph the exponential function f of x equals -3 times 3 to the power of x. After graphing, identify A and B, the y-intercept, and end behavior of the graph. Let's start with some values. We can plug in -2, 0, and 2. So at -2, that would give us 1/9, because we're going to square it and put it in the bottom. So 3 squared is 9, but it goes in the bottom because the exponent was negative, which turns into -3/9, or -1/3. At 0, 3 to the 0 power is 1. So then if we had 3 times 3 to the 0 power, that would be 3 times 1, or 3. Oh, -3. And if we had -3 times 3 squared, that would be -3 times 9 would give us -27. So we'll graph those. -2, -1/3, 0, -3, 2, -27. And this is going to create another curve. And now we need to identify A, which is -3. B is 3. The y-intercept is at 0, -3. And the end behavior, as x goes to infinity, as we move to the right, y goes down. And as we move to the left, y approaches 0. Graphing decreasing positive exponential functions. Graph each exponential function. After graphing, identify A and B, the y-intercept, and the end behavior of the graph. Choose several values of x and generate ordered pair. They did that piece for us. They've identified A is equal to 1 because there's that invisible 1 out front. B is 0.5. The y-intercept occurs at 0, 1. And as x approaches infinity, y approaches 0. As we're moving to the right, our line gets closer and closer to 0. As we move to the left, y gets closer and closer to positive infinity. F of x equals 2 times 0.4 to the power of x. Choose several values of x and generate ordered pair. 2 times 0.4 to the negative first power is 5. 2 times 0.4 to the 0 power is 2, because 0.4 would turn into 1. 2 times 0.4 to the first power would be 0.8. And 2 times 0.4 to the second power would be 0.32. A is 2, B is 0.4. Our y-intercept will be at 0, 2. Then we'll have to graph them to figure out what the end behavior is doing. -1, 5, 0, 2, 1.8, 2.32. So as x moves to the right, y is approaching 0. And as x moves to the left, y is approaching positive infinity. So if A is positive and B is a decimal between 0 and 1, or a fraction between 0 and 1, what is the end behavior of the graph? The problem that we just did has those attributes. So as x approaches infinity, y approaches 0, And as x approaches negative infinity, y approaches positive infinity. Graph the exponential function. After graphing, identify a, b, the y-intercept, and the end behavior of the graph. Let's start with a table. We can do -1, 0, 1, and 2. So for -1, we're going to do 3 times 0.5 to the negative first power. If you flip over a half, that gives you 2. So 3 times 2 is 6. Anything to the 0 power is 1, and 3 times 1 would be 3. To the first power, it leaves it as a half. A half times 3 would be 1.5. And then 3 times 0.5 to the second power. If you do a half to the second power, that gives you a fourth. A fourth of 3 would be 3/4, or 0.75. And now we need to graph them. So -1, 6, 0, 3, 1, 1.5, 2, 0.75. A is 3, B is 0.5, the y-intercept is at 0, 3. As x approaches infinity, moving to the right, y gets closer and closer to 0. As we move to the left, y gets closer and closer to the top, so that is positive infinity. So again, we are going to graph the exponential function and list all the same characteristics. This time we have f of x equals -0.5 to the power of x. Another way to write that would be f of x equals -1 times 0.5 to the power of x, because the negative is not in parentheses. If the negative were, like so, then the b value would be negative. But because the negative is not in parentheses, the a is what's negative and the b is positive. So they've written their list in the table, and they've found their outputs. They've graphed the ordered pair. A is -1, B is 0.5, the y-intercept is at 0, -1. As we move to the right, y approaches 0, but as we move to the left, instead of going up, now our end behavior is going to the bottom of the graph, so to negative infinity. F of x equals -3 times 0.4 to the power of x. Choose several values of x to generate ordered pair. -3 times 0.4 to the negative first power. Again, you can plug these into your calculator if you'd like, or you can do them by hand. It comes out to -7.5. -3 times 0.4 to the 0 power comes out to -3. -3 times 0.4 to the first power, -1.2. And -3 times 0.4 to the second power, -0.48. Identify those pieces in graph. A this time is -3. B is 0.4. Our y-intercept is 0, -3. Then we will need to graph those points. So as x approaches infinity, y approaches 0, and as x approaches negative infinity, y approaches negative infinity. based on the two problems we just saw, if a is negative and b is a number between 0 and 1, like a fraction or decimal, what is the end behavior of the graph? Well, as x approaches infinity, y approaches 0, and as x approaches negative infinity, y approaches negative infinity. For number 11, graph the exponential function. After graphing, identify a and b, the y-intercepts, and the end behavior of the graph. Use inequalities to discuss the end behavior. So I'm going to start out with -1. That would turn 0.5 into 2 because it would flip it over. 1/2 flipped over is 2. -2 times 2 is -4. Anything to the 0 power is 1, so -2 times 1 is just -2. To the first power, it would leave it as 0.5. -2 times 0.5 is -1. To the second power, a half turns into a fourth, and a fourth of -2 is -1/2. Then we will graph them. -1, -4. 0, -2, 1, -1, and 2, -1/2. Then put your curve through there. A is -2, B is 0.5, the y-intercept is at 0, -2. And then for the inequality aspect, we need to say something about if A is less than 0, and B is between 0 and 1, then as x approaches infinity, y approaches 0, and as x approaches negative infinity, y also approaches negative infinity. Why is f of x equals 3 times -0.5 to the power of x, not an exponential function? And this comes from the idea of different exponents having an opposite sign. So, for example, if we did -1 squared, that would be -1 times -1, which would give us +1. But if I did -1 to the third power, -1 times -1 times -1 would be -1. And then if I did -1 to the fourth power, that would give me +1. -1 to the fifth power would be -1. So we're bouncing back and forth instead of creating a smooth curve. So with this, even though it's not a -1 in there, we have a -0.5. With odd exponents, we would have a negative answer. But with even exponents, we'd have a positive answer. So we're getting bouncing back and forth between the negatives and the positives rather than creating that smooth curve. When an exponential function of the form f of x equals a b to the power of x is graphed, what does a represent? A represents the y-intercept.